Okay, so hello everyone. I'm Elbanna. I'm a master's student and I'm an intern at Logitech AI in Switzerland. And I'll be presenting the Logitech team that consists of Neil, Mikuláš, Pierre, and Milos. And I'll be discussing with you our submission, the Serab Byol-S model. So before we delve into the details of the model and how we adapted it, I wanted to share with you the origin of our submission. It was based on a model called Byol, short for Bootstrap Your Own Latent, and it was a model developed by a team in DeepMind, and it's basically an image representation learning model, and it learns the image representation in a self-supervised manner by building two different networks, online and target network that learns from each other and forcing the predictions from the online network to actually predict the representations coming out of the target network. And the inputs that are fed to both networks are kind of two different augmented views of the same input. And you can easily imagine how this can be transferred to the audio domain, and it did. And people actually, another team proposed the Byol for audio, which is the core of our submission. It follows the same training paradigm, but of course with the more appropriate augmentation steps. So to give you a more clear view of the model, we have the raw audio that we get the log-mil spectrograms, and then we go through the augmentation modules that actually you normalize the spectrograms and you do mix up, which is basically adding mixes of audio in the background. So you kind of, for the two copies you're generating, you kind of add the contrast to the background and leave the foreground consistent. And after that, there's a random resize crop that sort of approximates to pitch shifting and time stretching. And then you do normalization again to generate your final copies that will go through the encoder, projector, and the whole target and online network. So the way we adapted it was basically to retrain the Byol on a specific subset of audio set, which was related to speech. It was around 2K hours. That's why we called it Byol-S, Byol for speech. And the main purpose of doing this before the competition was to build a benchmark called Serab. It's a multilingual benchmark for speech emotion recognition. So we're basically targeting nine data sets with different languages and testing the different models, different pre-trained models, and seeing the performance between them to create the benchmark. And as you can see here with previous models on literature, the Byol-S managed to outperform across the 9 data sets, and also outperform the original Byol itself because it was more specific to speech. So the other adaptation that we have done for the submission was, as we all know, the scene embedding approach and the timestamp embeddings. In the scene embeddings, we basically generated the embeddings from the entire audio clip. So we have the audio tensors, and for each audio, we generate their corresponding spectrograms to feed it to the model and generate the utterance embeddings. And that was nice because the model was basically accepting variable length of audio. So this was not an issue for us. But in the timestamp embeddings, this was actually our first time to test Byol-S on a timestamp related task. So the way we did it was basically breaking down the audio into chunks of 1 second with a hop size of 50 milliseconds, because the way we picked these parameters was that when we trained Byol-S was basically taking 1 second of the input data and pass it to the augmentation modules. So that's why we wanted to see how it will perform if we broke down to 1 second, because currently we'll be performing more experiments to see the minimum size of audio that would still preserve the information and Byol-S would not fail in this sense. So just for a test, we submitted this version of it. And at the end, we will generate the window embeddings for a specific audio with the corresponding timestamps, of course. So in terms of results, we have seen that Byol-S performed really good in some speech-related tasks and music versus speech. And we have seen that in the case of the timestamp related embeddings, which was kind of expected that it performs less. However, the way we were trying to interpret the results was basically that we said that Byol-S performs best on speech, music related, or environmental sound classification related tasks, because it was trained on spontaneous speech audio clips, like from the audio set from YouTube. So basically, it's not pure anechoic speech. There's some sort of music and environmental sounds in the background, so that could be a reason. And also, the main purpose that it worked on emotion recognition and related paralinguistic tasks was because this was the main intention and the main purpose. And also, I would assume that because I think Heinrich also mentioned it, why would a speech-related task trained on audio set would actually perform good on emotion recognition? My assumption would be that the spontaneous clips from audio set actually kind of capture a huge range of emotion and affection. So it could sort of learn this during the process. And that's how we have proved it in Serab, a related emotion recognition benchmark. It kind of performed bad in case of language classification related tasks. And maybe it was because it was trained on English bias dataset. Although on the Serab, it was multilingual, but yet it outperformed the previous models. So that's something also worth thinking about. The final thing was related to the timestamp related tasks. And as I told you, it was not tested yet. So was expected that we're not sure how to limit Byol-S for picking the perfect window size. And that will take us to the final part, which is our future work and basically the current work that we're doing now, which is studying the context window, the minimum window that Byol-S can still preserve information and perform relatively well. And this would be, of course, useful for the timestamp related tasks. Also, we are curious about hybrid representations because we have tested Byol-S on other downstream tasks related to a cognitive load, a data set in our company. And we have seen that DSP-based or handcrafted features perform surprisingly well across and compared to previous pre-trained models, which is quite interesting. And that's why we're kind of doing a hybrid training paradigm between DSP-based and like data-driven based features to see how can we leverage both information. And also ablation studies towards augmentation, including the frequency component to make it a 2D augmentation module or 1D on the raw audio. And we're also testing on different emotion recognition button regression tasks like estimating arousal and valence to see, we just want to see how Byol-S can perform on these wide tasks, and also playing around with the different types of encoders to compare in terms of performance, and also try to retrain the Byol-S on different languages to kind of reduce the language bias, and also different setups like more spontaneous speech, scripted speech. So basically Byol-S can capture more features in that sense. And thank you so much. And looking forward to the Q&A session.